All right, let's continue our discussion by talking about measuring voltage. So when we have a simple circuit like so, we can measure the voltage by hooking up a voltmeter um, across the resistor, so before and after the resistor, and with that voltage drop here, okay, when we measure that voltage drop before and after the resistor, that difference, that is going to be the voltage that's being supplied by that battery or your voltage here, okay? So we have our battery here and our resistor, our voltmeter, okay? And so this voltage drop, or that delta V voltage drop, will provide us with the output voltage of the battery. Okay. Okay, and this down here is just an example when measuring that. So if we get some voltmeter voltage drop of 18 volts, that will be our voltage that's supplied to this simple circuit. Okay. All right, so this has a lot of information here, but bear with me. We are going to look at the resistance and how that's dependent on the material, the type of material, and the shape of the object, okay? So for example, let's look at a uniform cylinder of length L and cross-sectional area A, as so. Okay, so we have some length L, a cross-sectional area A, oops, A here, okay, and look at some of these relationships. So if we have a longer cylinder here, so as that length increases, so longer cylinder, there's going to be more collisions of the charges um, so the charges will collide more with its atoms, okay, because there's more space to do so, okay. The greater the diameter and therefore the area of the cylinder, so the greater the diameter of the area, the more current it can carry, okay. So as this area increases, it can carry more current through the material, okay. So that's all about the shape dependence and a little bit on the material dependence. So this is going to be similar to the flow of fluid through a pipe. So like liquid or water flowing through a pipe, okay? Now let me show you table 20.1. Let me pull that up here. That's going to be in the next section. Bear with me, guys. So we're talking about resistance. Oh, here we go. This section here. So based on whatever the material is, we will have a different resistivity value. Okay, so this row here, that is called resistivity. My dog's going crazy, if you can hear her, sorry. And so we can see a lot of different conductors here. They're very good at transferring the charges, and then we've got semiconductors here, and then insulators here, okay? So these are all the values of rho, or the resistivity, okay? Now let's look at that. Whoops, did not mean to do that. There we go. Let's look at the resistivity, rho, of a substance. It's an intrinsic property, so it's independent of shape or size and proportional to the resistance of an object, okay? So remember that an intrinsic property is something that is independent from other things. Okay, so like mass is intrinsic. Okay, that's an intrinsic property. So again, for this resistivity rho, it's going to, excuse you, my goodness. I'm sorry. The resistance of an object here can be calculated as so, given some resistivity of an object, whatever that substance is, the length, and the cross-sectional area. Okay. All right. And then I want to show you guys a simulation, another one here. And this one is going to be very similar to the other one I was showing you. So if we start changing some of these values, what's going to happen to the overall resistance? Okay, so if we increase resistivity, our resistance will increase. Let's put that back down. If we increase length, resistivity is going to increase as well. Okay, increase area, our resistance is going to lower. Okay, we're going to have a lower resistance. And then we can look at the complete opposite. Woo! If we lower the area, we'll have a higher resistance. Lower the length, lower resistance. Lower resistivity, lower resistance. Okay? All right. Okay, so you can play with that on your own time as well to kind of get a better understanding. Okay? All right, so let's look at a quick example here. So this is example 20.5. A car headlight filament is made of tungsten and has a cold resistance of 0.35 ohms. If the filament is a cylinder of 4 centimeters long, what is its diameter? Okay, so let's go back here. Cold resistance, so we know R is 0.350 ohms. Our diameter is what we want to know. We need to know our resistivity rho of tungsten. We need to look that up in that table. The length is 4 centimeters long. Okay, so let's quickly look up rho for tungsten. So go back to here. Tungsten resistivity, 5.6 times 10 to the negative 8th. Okay, 5.6, 10 to the negative 8th. And then what are its units? Something I need to look up. It is ohms meters. Ohm meters. So ohm meter. Okay, so we will need to convert this guy into meters. So this is going to be 0.04 meters. Remember that we have a cylinder here, and so we will need to find the cross-sectional area of the cylinder, which will be the area of a circle, or pi r squared. Okay, so that's the area of a circle. And this is going to give us our radius. Okay, so eventually we will need to use that diameter is equal to 2 times the radius. Okay. Okay, so that's a lot of information we've got there. But let's backtrack and find the formula that we need to use. So that is this resistance formula. So R is equal to rho L over A. R is equal to rho, That's not row. Rho L over area. Okay. So we'll have A, because that is where our diameter is. It's within the area. It's equal to rho L over our resistance. Okay. And we can start plugging in now, or we can hold off. I'm going to hold off. Let me actually put this into another term. So we've got R is equal to D over 2. So this is our radius. Okay, but we're looking for a diameter of that filament. Okay, so let us plug all of that into A. So we have pi r squared. So that is D over 2 squared. Okay, and that's going to equal rho L over R. Okay, all right. We can keep going. So I'm going to do that. Again, if you feel more comfortable starting to plug in your numbers here, feel free to do so, okay? I prefer to wait until the end to plug stuff in, okay? So we will have D squared is equal to, and I'm going to pull over my constant. So this pi and this 2, I'm going to pull those guys over. So I have 2 squared over pi rho L over R, our resistance. Okay, then we'll square root both sides, so we get D is equal to 2 over, actually, let me put it this way, 2 times rho L over pi R, resistance, and all of that is in a square root. Okay, all right. So now we can start plugging stuff in. So we've got D, our diameter, equal to 2 square root of rho, which is given up here, is 5.6 times 10 to the negative 8th ohm meter, times our length, which is 4 centimeters or 0.04 meters, times pi, times our resistance, which was given to us as 0.350 ohms. Okay, so we can quickly look at this and say, okay, our ohms cross out. That's good. And then we'll get a meter squared here. That's under a square root. So we will end up with a value in meters. So this all looks great. So let me get my calculator out and start plugging this in. So 5.6 times 10 to the negative 8th times 0.04, oops, divided by pi times 0.35. Okay, and then we'll square root that guy and multiply it by 2, and we get a diameter of 03 times 10 to the negative 5th, and this is in meters squared. Okay, we can also change this into centimeters. That might look a little better. So to change this into centimeters, I'm going to go ahead and kind of put a little space here. What we'll need to do from meters to centimeters is multiply it by our value by whatever we have. We have 1 meter, and there are 100 centimeters in 1 meter, and then square that. Okay, so we'll need to multiply this by 100 centimeters squared. Okay, I'm going to multiply it. And I get a value of 0.903. This is in centimeters squared now. Wait, I'm sorry, that's not right. Hold on, back it up. Hold on, this is not squared. We found our diameter. So we need to erase all of that. Okay. Yeah. Why don't we actually get it in millimeters instead? So what we have here is in meters, right? So under the square root, we have meters squared, and then we square root that, getting meters, which is good. Those are the units we're looking for. So to get to millimeters, let's say 1 meter times millimeter. Oh man, that's hard to read. Let me get red out. Right, there are 1,000 millimeters in 1 meter. Okay. All right. And then, so you multiply. So let's do that. And then multiply by 1,000. And we'll get 0.0903. And this is in millimeters. All right, so this is my diameter of this filament. So very, very thin. Okay, this is my diameter. Okay. All right, so let's go ahead and move on. Actually, this is where we're going to pause, and then we'll pick up in the next video talking about temperature variance with resistance.